Good day, I'm Vincent Saxtetter, and this is the After the Age of Fire channel. Today is September 20th, 25, and this is episode 8. Um, Today I'll be talking mostly about energy and a way of measuring energy called the calorie. But first, I want to talk about numbers and why numbers are so important when you're talking about the reality around us, say the amount of energy that we use, or the amount of energy in in the wind or in nuclear power or so on. And and because throughout this channel, the content in this channel, I'll be talking about numbers all the time, at least during the first half, and then toward the end I'll move more into things connected with history and with culture and with morality and religion. But at least during the first half, 2/3, there will be an awful lot of content uh, pertaining to numbers. And I want to say why they're important. I think I already talked in a previous episode that's very important to pay attention to the reality around you before you think about what you're going to do about it. And numbers are a very fundamental way of paying full attention to the reality around you. You need to keep track of a lot more than numbers. Numbers don't give you a good handle on beauty, for instance, or right or wrong, or any number of other things. But but if you really want to understand what the chair in front of you is like, you'd better know how tall it is, uh, whether it's uh, a meter high or 10 meters high. Um, so and I think it has a lot to do with respecting. If you're willing to respect something or someone, you have to keep track of numbers. For instance, if I were to buy shoes for my wife, and the shoes that I buy are always one size too small, you might think that I don't care for my wife that much. Or if I were to invite 10 guests and prepare food only for three, you might think that I don't have that much concern for my guests and I'm not really that friendly toward them. Same thing if I said I know somebody, but I didn't notice that they were missing an arm or they had only 9 fingers or they were missing an eye um, or if I didn't know how many sisters and brothers they have, then you might think I don't really know that person that well. Um, Numbers really matter if you want to really respect something, if you want to see it for what it is, or the person for what they are, who they are. Um, you have to know more about the person than just what they said yesterday. You have to have a good look at them and see what they're like. The same thing, and not just whether they're pleasant or not, but you certainly want to have an idea of how big they are, whether you're looking at a toddler or an adult, and things like that. Um, um, and for caring for somebody, again, if, for instance, if I were to feed an adult 1,000 calories a day, they would progressively starve. On the other hand, if I fed them 2,000 calories a day, they'd be more or less fine. Numbers are really important, and that's why I think we have to keep track of the numbers of the world around us before we decide what we're going to do about it. Um, so, in particular, I'll be talking about calories, which are a way of measuring energy. But before I get to calories, I want to say that that throughout this content, I'll be using the metric system, not the United States system. The metric system is things like meters um, and degrees Celsius, and the United States system is things like feet and yards and miles and degrees Fahrenheit. And what comes naturally to me as an American is, of course, the degrees Fahrenheit, the feet, the inches, the pounds, and so on. But in order to reach the most people with this channel, most people just have little or no experience with feet and pounds and degrees Fahrenheit. Most people around the world have experience with the metric system, so I'll be using the metric system. Uh, and there are some rules of thumb that can help you a lot. For instance, um, 2 pounds is roughly a kilo. Um, and you could also say 2 degrees Fahrenheit is roughly a degree Celsius. Um, and things like that. When appropriate, if I can remember, I'll try to tell you as I go what something is in pounds or feet. But I won't be doing it that often because it would just get tedious and it would slow everything down. I can't always say something in meters or in feet. Um, it would just be awful. So I'll go on like that, but just the one exception though is I will be talking as far as energy goes. I'll be talking about calories, and the reason why I'll be talking about calories and why the rest of this episode will be about calories is because it's the unit of energy. It's the way of describing energy that everyone around the world uses to measure the energy in our food. Um, it's the number that's printed on your food labels, and it's the number that you think about when you wonder about whether you're eating too much. Um, so I want to bring the numbers that we talk about as close to home as easily understandable. So I'll be using the only unit of energy, the only way of describing energy that almost everybody has some experience with, which is the calorie. This is not actually the metric system. The metric way of measuring energy would be the joule, but nobody talks about joules in daily life. It's on no food wrappers. Calories are. So that's why I'm talking about calories. And I'm going on about this in this episode because calories, maybe some people may not have thought about this a lot, but calories don't just describe the amount of energy in your food, they can describe all sorts of other things. And to make that point, I'm going to talk about the number of calories that you have when you're in motion, or the number of calories that you gain by standing up or by falling down and things like that. I just wanted to just make the point that calories are energy, and not just food energy, but any kind of energy can be measured in calories. So it won't be a surprise to you later when I talk about the number of calories coming from the sun every day. Um, so the first example is kinetic energy. That's the energy you have from being in motion. Okay, and an adult, and I'm talking about an 80 kilo adult. That means roughly 175 pounds, 180 pounds. If they're walking at a reasonable pace, they'll have 1/40th of a calorie in kinetic energy. That's how much energy is embodied in their body just by walking. On the other hand, if they're sprinting down a race course, it'll be between 1/2 and 1 calorie. So, of course, they'll be spending a lot more energy to keep themselves going, but just the amount of energy that they have in the motion per se would be between 1/2 and 1 calorie. Now you take that same person and you put them in a car and you go down the highway at highway speeds, then that same person will have, just by moving down the highway, more like 8 calories. Um, sorry, yeah. Um, Now the car that they're moving in at highway speeds will have around 100 calories. A 1-ton car. Now a metric ton is roughly not quite the same as a United States ton. Um, so that car, as it's moving at highway speeds, will have 100 calories. The passenger will have 8 calories or so in kinetic motion. Um, so the car will have roughly the same amount of energy as 1/2 of a candy bar, and the person will have roughly, moving at highway speeds, it will have in kinetic energy roughly the same as a couple of almonds um, of energy. Now, moving on to other things, how about a bullet? Now, a bullet fired from a handgun will typically will have between 1/20th of a calorie and 4/10ths of a calorie, depending on whether it's a pistol and how much, or some other sort of gun, and how much gunpowder there is in the bullet, in the cartridge, and things like that. But 1/20th of a calorie in a bullet is already more than enough to kill somebody. It just has to be delivered to the right place and delivered very quickly. 1/20th calorie, even though we eat thousands of calories a day, 1/20th of a calorie in the right place at the right time can kill. Um, Now, a long range gun, a rifle, a hunting gun, a long range rifle or hunting gun can contain 1.5 calories. That's something for killing elephants or for snipers. So a calorie or two is more than enough to kill a large animal. Um, Going back to handgun bullet, which might have 1/20th of a calorie or more. On the other hand, if you deliver the same amount of energy in a little bit of a different way, suppose you have pro boxers, and one punch from a pro boxer might contain between 1/20th and 1/10th of a calorie, and that typically doesn't kill if the other guy is well trained and has good protection on. Um, so it's the same amount of energy as in a typical handgun bullet, but it doesn't kill partly because of the training and partly because a punch delivers energy over a wider area and takes a little longer to deliver that energy than the impact of a bullet. Um, Baseballs also contain a similar amount of energy. A typical Major League Baseball might, if given a good hit, have 1/30th of a calorie in it. Now, baseballs do kill, maybe several deaths a year. If you want to see an interesting list of discussion of different deaths from baseball, read Death at the Ballpark. It's a published book. Um, I don't know, I haven't read it myself, but I understand that it lists many different deaths at the ballpark from hitting by baseballs. Um, Now moving on to falls and gravity. So if you take an adult, the same 80 kilo adult, 175-pound adult, you have them lying prone on the ground, lying on their back, whatever, and then they stand up, that will require about 1/5 of the calorie to go from lying down to standing up. And similarly, if they were to fall down again, that would mean they would lose 1/5 of the calorie uh, of gravitational energy, um, and that calorie has to go somewhere. Typically, it turns into heat, but it could be that on the way down they break a leg or something. Um, on the other hand, so 1/5 of the calorie from falling typically won't hurt you much, except for maybe breaking a bone if you're not prepared and careful. On the other hand, a 5-meter fall, that would be about 1 calorie, could kill, but certainly could easily hurt you. 5 meters means 5 yards, roughly 15, a little more than 15 feet, I know a little less than 15, around 15 feet. And a 20-meter fall, that means an adult losing that's 4 calories of gravitational energy. A 20-meter fall will hurt you very badly more often than not, and will very easily kill you. Um, so I already covered gravitational energy. One more thing, a calorie is the same amount of energy as if you took 430 kilos, a half ton roughly, and you raised it 1 yard, 1 meter. 1 meter, 430 kilos, 1/2 ton, 1 yard. Or if you took 1 kilo, 2 pounds, and you raised it 430 meters, 430 meters would be around a quarter of a mile high. That would also be 1 calorie. So you have to do a lot of lifting in order to use up a calorie. Of course, pushing it all the way up may take some more energy, it will take some more energy, but the amount of energy that's stored by keeping something high versus low isn't that great. You have to have very heavy things, but of course, for instance, water flowing downhill, the reason why it contains so much energy is because it's heavy. Water is really heavy. So we've covered gravitational energy, the number of calories in gravitational energy, and in kinetic energy, that's energy of movement. Now I want to move on to heat. Okay, how much energy is in heat. And to do that, I want to set up the question a little bit. I want to talk about the amount of if you put 1 calorie in 1 kilo of something, and I'll talk about the different substances. I'll go over through a number of substances. You take 1 calorie, you have 1 kilo here, you add that calorie to that kilo, how much will the temperature go up? Because heat energy just means the amount of energy that's stored in temperature, in your temperature. Uh, so if a kilo again is roughly 2 pounds, 2.2 pounds, something like that. Um, so if you take 1 calorie, how many degrees Celsius will the temperature go up? So maybe I'll try to give roughly how many degrees Fahrenheit that is. But anyway, you multiply by a little less than 2 to get from Celsius, a change in temperature Celsius to get to the change in temperature Fahrenheit. So so gold and silver, they're metals. In general, metals react very, very strongly to energy. Their temperature changes a lot. Or another way of saying it is that they don't store energy very well. So if I take a kilo of gold or silver, suppose I'm that rich, and I add 1 calorie to that kilo, then the temperature will go up by roughly 32 degrees Celsius. That's roughly 58 degrees Fahrenheit. So you don't need a lot of calories in order to melt gold or silver. Now, copper, the other metals, I'm going to go through a spectrum. This is in other words, I just talked about a material. This is gold and silver are the materials that among the ones that I list here that react the most strongly to input energy, and I'll go down to the one that reacts the least strongly, which happens to be water. But I just want to give you an idea of where things are on that spectrum. So gold and silver, the temperature will go up by 32 degrees Celsius, roughly 56 or so degrees Fahrenheit. Copper, much less. It'll go up by 11 degrees Celsius or 20 degrees Fahrenheit. You take your kilo of copper and you add your calorie, and it'll go up. The temperature will go up by 11 degrees Celsius. Iron and steel are a little bit less, and chromium, they only go up 9 degrees Celsius. Titanium, 8 degrees. So these are typical numbers for metals, somewhere between 8, 9, 11, even up to 32 degrees temperature increase. Now let's move away from metals and let's talk about most dry, hard solids. So for example, asphalt, concrete, salt, brick, marble, granite, glass, dry soil, really dry soil, it has to be really dry, charcoal, sand, all of these things. Most dry materials and hard ones, of course sand is not really hard, but including the hard ones, their temperature will go up by 5 or 6 degrees if you add. So 5 or 6 degrees will be still roughly 5 or 6 degrees Fahrenheit. No, sorry, it'll be roughly 5 or 6 degrees Celsius will be roughly 10 degrees Fahrenheit. So you add 1 calorie to a kilo of these hard materials and their temperatures will go up by 5 or 6 degrees Celsius or 10 or 11 degrees Fahrenheit. Air holds energy. You have to put energy into air in order to make it hotter, and you have to take it out to make it colder. So I'll talk about energy. 1 kilo of air, and this is of course air's the amount of kilos. The density of air depends on the temperature and on whether the air is at ground level or up at mountain, somewhere high up on a mountain. But let's talk about at sea level. Air at sea level, no water in it. 20 degrees Celsius, that's around 75 degrees Fahrenheit. Um, and I'm talking about uh, a cube that's 94 centimeters on a side. That's roughly a foot on a side, roughly a yard on a side. So 1 cubic yard of air. That cubic yard um, or a cubic meter will weigh 1 kilo. Um, so I add one calorie to that kilo of air, and I'll find that the temperature goes up by 4 degrees Celsius, or by 7.5 degrees Fahrenheit. So it contains it holds heat energy a little better than solids, and much better than most other solids, especially the hard ones, and much better than the metals. Now we go further down the spectrum, and we talk about some other materials: oven dried wood, clay, leather, sugar, flour, and those, food materials, dry food materials. Most of these will go up by 3 degrees when you add a calorie, 3 degrees Celsius. And then you talk about the oils and the things that are like oils, like gasoline, alcohol, paraffin, fats, and then strangely enough also ice and rubber. These guys will go up typically about 2 degrees Celsius. When you add 2 degrees Celsius is 3.5 degrees Fahrenheit. Um, when you add your calorie, that's how much the temperature goes. So they're much better at holding holding heat energy than most other materials. But the best of all is water. Water, and this is the definition of a calorie, scientific definition of a calorie. If you add 1 calorie to 1 kilo of water, the temperature will go up 1 degree Celsius, or 1.8 degrees Fahrenheit. So water is one of the best materials you can find for holding heat. It reacts least strongly of just about any material on the face of the planet to heat. Its temperature goes up and down very slowly compared to the amount of heat you put in it, and that makes a world of difference. Our world would be completely different if water weren't so good at holding heat. Um, and it's also when you turn water into water vapor, into steam, it's also great at consuming energy, you need about to change a kilo of water into a kilo of steam. You need about 500 calories, which is just a lot of energy to get a little bit of water and turn it into steam. Um, so um, Now there are a number of materials that like if you have a lot of water in something, like in the human body, um, their ability to absorb heat energy will be similar to that of water. For instance, the human body, if you add a calorie to a kilo of the human body, people have studied this. That the human body's that kilo of human body's temperature will go up by 1.4 degrees Celsius, which would be about 2.5 degrees Fahrenheit. Um, so this also is of huge significance to our life. The fact that our bodies don't heat up that fast compared to many other materials. Um, Now I want to talk about a little bit different thing. I want to talk about, suppose you are lying in the sun, sunbathing at noon on a warm day with the sun above you and high, I mean, at its zenith, just above you, shining right down on you, so you're absorbing a lot of sunlight. Uh, Over an hour, your body of an adult will absorb somewhere around 330 calories from the sunlight hitting you. Okay, and even though our bodies don't heat up that fast, it will heat up. So your body will heat up if you were dead, not if you were just sitting there in the sun and dead and not reacting to the heat in any way. Your body would heat up by 6 degrees Celsius or 11 degrees Fahrenheit um, over the course of that hour. So you can imagine it wouldn't take many hours before you just start to cook. Okay, and already 6 degrees Celsius or 11 degrees Fahrenheit is enough to make you really, really sick. Okay, so you wouldn't sunbathe long at all. Um, but the fortunate thing is that because it takes so much energy to turn water into water vapor, all you have to do is sweat a little bit to get rid of that energy. So the sunbather, if they're sweating, if they manage to sweat 600 milliliters, let's see, that's a liter is around a quart, so that would be somewhere between 2 and 3 cups of water. If that sunbather sits there for an hour, and over that hour they manage to they're drinking their water or their soda, and they sweat 2 or 3 cups of water over that hour, they'll be just fine. Um, they'll sweat away all the energy that they get from the sun, and in fact that brings us to the fact that among all the mammals, humans are the best at sweating. It's a huge thing. It's really a huge thing. We also stand up. That means that we have a lot less area exposed to the sun usually than animals are. Most mammals are on all fours. We expose only our shoulders and our head to the sun as we're walking underneath it at noontime. So we're absorbing less sunlight in the first place, and we're great at sweating. And that means we're great at keeping ourselves cool in hot weather. We're better than any other mammal and probably any other animal, except maybe the insects and things, at keeping ourselves cool in hot weather. That means that we're better at, we can, even on the hottest days at noontime, if you're properly accustomed, you can keep moving, working, and moving fast, pretty fast, and also working all through the day um, outdoors. And this has given us a huge advantage and opened up many possibilities for us that just are not possible for other animals. In particular, millions of years ago, when we and our ancestors were living in Africa, we were we were able to move farther and faster than any other animal because we could keep moving throughout the day without stopping. As long as we could pick up some water here and there, we could just keep going. Um, and so even an animal that was quite a bit faster than us would have to stop and pant in order to cool themselves down. And sooner or later, if we just kept tracking that animal, we could, on the long run, move faster than any other animal actually on the planet, any land animal on the planet, and at least in hot weather. Specifically in hot weather, because we don't have to stop and pant. We could hunt down any animal and we could kill any animal. It was huge. But there have been many other advantages. We are just better at long distance movement in hot weather than any other animal. Except maybe birds, I guess. Um, but so that's heat. So we've covered heat, we've covered gravitational energy, we've covered kinetic energy. These are calories, and I hope this is opening up new perspectives on the word calorie for you. That's the whole point of this, and we'll cover two more. One is chemical energy, the energy that's stored in chemicals, and the last will be nuclear energy. Um, so now, for chemical energy, I'll spend a lot of this talking about how much energy is stored in a gram. Um, of chemical energy. I'm not talking about heat energy. Uh, materials, the right chemicals are much better at storing energy chemically than they are than anything is at storing it as heat. Um, so um, uh, now a gram. What's a gram for us Americans? Uh, well, if you wanted a gram is 28 grams is an ounce. So if I tell you that something will that that a particular uh, substance, like say um, lean meat, lean meat stores about a calorie per gram. That means about 28 calories per ounce, or uh, there's around 450 grams in a pound. So lean meat, one calorie per gram, 28 calories per ounce, 450 calories per pound. So you would, and all these numbers, which will be calories per gram, you just multiply by 28, or if you like 30 to get the number of calories per ounce, and you multiply 450, or if you are sloppy, 500 to get the number of calories per pound. Um, so um, alkaline batteries, the batteries that you buy at the store, um, and also the lithium ion batteries that are in your cell phone or your computer or your car, they store between 1/10 and 1/5 of a calorie per gram. And I'm going in a spectrum again. I'm going from the least amount of energy stored per gram up to the highest amount of energy stored per gram. The highest will be things like natural gas and gasoline. But 1/10 to 1/5 of the calorie per gram uh, in our batteries, at least the batteries that we deal with most often. And so now an AA battery, the ones that you buy at the store and you put in different devices, uh, your toys and your flashlights or whatever, they weigh about 23 grams. So one of those will store between 2 and 4 calories. Um, and now next step along this is TNT is like lean meat. TNT, the explosive, that stores about a calorie per gram. Um, so 5 or 10 times what a battery does. But the advantage of TNT is that it can release all that energy really quickly. That's why it makes a great explosive. Gunpowder can store between 1 and 3 calories per gram. Just to remind you that to get the number of calories per ounce, you multiply by 28. To get the number of calories per pound, you multiply 450. Okay. The lowest grade coal, something called lignite, it's almost crumbly in your hand. Um, that stores 3 calories per gram. Um, uh, then next step up, dried foods. Any food that's not high in oil and has been completely dried out. Um, Say like beef jerky or banana chips or wheat flour, um, or sugar, table sugar. Those all basically any dried food, as long as it doesn't have oil in it, will be 4 calories per gram. Now it can be that one thing that complicates a little bit, but I just want to say when people talk about calories and then you wonder whether some food has a certain number of calories and versus another food, what's low calorie and what's high calorie, almost all of that is about how much it's been dried out. Um, if you have a potato and you dry it out, and if you have a piece of meat and you dry it out, and you have a vegetable and you dry it out, it doesn't matter what the material is as long as it doesn't have much oil in it. It'll come out to having about 4 calories per gram. That's that's like 110 calories per ounce. That's like 1,800 calories per pound, whatever the material is, whatever the food is. It makes things very simple if you're just willing to keep track. Now, there's one fly in the ointment. There are some, especially the vegetables, contain some amount of plant material that's really not something that we can digest, and those uh, those plant materials um, those plant materials that's called fiber, and we can't digest it, so we don't get all the calories. So it can be that you're eating, say, broccoli, and some percentage of those 4 calories per gram of dry plant material is not something you can digest, so you get less out of it. Like grass, you dry grass, you get hay, 4 calories per gram, but we can't digest it at all. So we as a species can get 0 calories from it. Horses and cows can get something from it. Okay, so all dried plant materials contain about 4 calories per gram, which is around 1,800 calories per pound. Um, Whether we can digest it or not is a different matter. That includes hay, dry wood, and so on. Um, there's a higher grade coal called subbituminous coal, which has around the same 4.5 calories per gram. Then we move up, next level up, uh, beyond dry food materials, leaving out the oils. I meant dry food materials that don't have oil in them. Now we move up to the highest grade coal called anthracite. It's very dark, black, and solid. It's almost pure carbon, and that contains about 8 calories per gram. So about twice as much as what is in, say, wheat flour or most dried plant materials. Um, and then there's animal fat and cooking oil. Uh, these are the best way of storing energy in food that we can actually digest. Those contain about 8.8 calories per gram. Any animal fat or cooking oil, it's about 2.2, a little more than twice the amount of energy in other dried plant material. So um, the thing is that in general, dried plant material, we don't usually eat dried plant material. Usually it's mixed with water, and or it hasn't been dried out yet, say in fruit, and then that's why cooking oil seems to have so many calories in it. It's not really, it only has gram for gram compared to dried plant material. It's only roughly twice as much, a little more than twice, but compared to, say, undried fruit or vegetables or meat, it may be 10 or 20 times as much, um, because the undried materials have so much water in them. Um, Next level up, uh, there's crude oil and anything you can make from crude oil, gas, diesel, jet fuel, paraffin, and many of the plastics, polypropylene, polyethylene. So some of the most common kinds of plastic. They have 11 calories per gram. Uh, and then the highest that I'll mention here for storing energy is natural gas. That's 13 calories per gram. Um, so we have a spectrum that runs from say the oils and natural gas, which are up around 10, all the way down to batteries, which might be 1/10 of a calorie per gram or 1/5. Um, so that, I mean, you need, compared to an AA battery, you look at the amount of energy in an AA battery, you could maybe store the same amount of energy in an amount of oil that is 1/100th the weight. Or in other words, you would need 100 AA batteries, each 23 grams, so that's 2 kilos, more than 2 kilos, to store the same amount of energy as in maybe 23 grams of oil, um, or in 50 grams of dry plant material, say wheat flour or corn flour or rice. So there's a big range in chemical energy densities. But I just wanted to give you a handle on that. Now I want to talk a little bit about food, because foods, as I mentioned, they do contain water. They aren't all dried out. So you have the fats and the oils, 8.8 calories. Then you have alcohol. Alcohol is near the fats and oils. It's chemically not so different. That's 6.9 calories per gram. So if you want to get fat, drink a lot of alcohol. This is the pure alcohol. Of course, it's watered down in beer and wine and so on. Nuts, 6 calories per gram because they have so much oil in them. It can vary a bit from nut to nut. Um, then there's the dry foods, around 4 if they're dried out. Bread, bread has some water in it, 2.7 calories per gram, roughly, depending on the bread a little bit. Then there's lean meat, around 1. Then there's bananas and tofu, and I think potatoes are around 0.9. It can change a little bit depending on the potato. Apples, 0.6 calories per gram. Uh, Now, one way to read this is this can predict for you if you were to take an apple and dry it out how much. Suppose you have a kilo of apples and you dried them out. Uh, Suppose you completely dried them out. How much would they weigh after you dried them out? It would be around 150 grams. And those 150 grams would be about 4 calories per gram. But before you dry them out, you'd have a kilo there, and you'd have 600 calories there. So, and then whole milk and Coca-Cola, the soft drinks, I think are generally around 0.4 calories per gram or 400 calories per liter, because they're liquid. um, so that covers chemical energy. That's the energy that you can store through and chemical bonds and release. Um, so the last thing to cover is nuclear energy. Um, now, because the basic idea is that anything that weighs anything, that weight is equivalent to an amount of energy. Um, so if you can get rid of the weight and turn it into energy, you get some energy out. Now, the thing is, we can't actually turn an atom completely into energy. There's a physical law that says you start with one atom, you're always going to have at least one atom. Or you can combine them, or fission them, but you can't. You aren't going to change the mass of the atom very much. You can change a little bit though. So one way of doing that is called nuclear fission. It's where you take an atom's nucleus and you split it into two other nuclei, and uh, the two nuclei at the end will weigh just a tiny bit less than the nucleus that you started with. So, say uranium, break it into two other elements, and it will lose about 1/10% of 1,000th of its mass, and that 1,000th of its mass will turn into some energy, um, and actually quite a bit of energy. It's only 1,000th of the mass of the original uranium atom that turns into energy, but it's plenty for our needs. And then in a nuclear reactor, you take the uranium, and we actually only use up about 5% of the uranium in the reactor before it's no good for our purposes. It becomes dirtier and dirtier as we use it, and so after about 5% of it is used up, 95% of it is still there that would be usable, and except for the uranium fuel has now gotten dirty, and so we have to throw it away. So so we're actually using 1,000th of the uranium's mass, and then 1/20th of that uranium. So 1/20,000th of the uranium's energy, if you could convert all of the uranium into energy, which you can't, is actually getting turned into energy, but it's still a lot. Okay. So suppose I have uranium that I've mined and I've purified and I've gotten it ready for the reactor, and even keeping only that 1/20,000th of the theoretical energy of the uranium, even using only that 20,000th, still 1 gram of uranium will give me 1 million calories. So 1 million calories. Compare that to wheat flour. 1 gram of wheat flour stores 4 calories. 1 gram of natural gas stores 13 calories. 1 gram of uranium ready for the reactor stores 1 million. So it's an immensely better way of storing energy. It has its disadvantages, of course, like radioactivity, but I'm just talking about in terms of the amount of energy you store you get from that uranium. You need very little uranium to get a huge amount of energy. That's why we have things called bombs, nuclear bombs. and reactors. Now, of course, the uranium that you get out of the ground is not, the ore is not pure uranium. Now, some mines are very high grade ore, more than 1/10 uranium. For instance, the Cigar Lake mine in Canada, if you mine that, actually it's a little less than 1/10. If you that ore, it's like 1/14 uranium. The ore is. So that ore, as it stands, just in the ground, has about 70,000 calories per gram. Compare that to coal. You mine coal, you mine anthracite, the highest grade coal, that's 8 calories per gram. You mine the lowest grade coal, that's lignite, that's 3 calories per gram. Uh, the Cigar Lake mine produces its uranium ore contains 10,000 times more calories per gram than coal. So if you happen on a load of uranium ore and you know what to do with it, you're in business. It's much more. You just don't have to move much around. Don't have to dig very much. You get an awful lot of energy out. Now, not all uranium ore mines are so high density, so high grade ore. For instance, the Olympic Dam mine in Australia, if you mine that ore, it's 500 calories per gram of uranium ore. That's still 100 times more than coal, so it's still a very good source of energy if you know what to do with it. Okay, so this is all just to give you an idea of what a calorie is. My main point here is just to hammer it into your head, in my head, that 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 calories are not just about food. That everything, whenever you talk about energy, you can talk about calories, and so that there won't be any. I hope that in the next episodes you won't have any sticker shock or whatever when I start talking about the number of calories coming from the sun or stored in that a dam can store in water and gravitational energy in the water that's held behind the dam or in a spring or whatever. Um, that's it. And also because I think numbers are important. If you want to know the real world, you have to know about numbers. And our best way of the way that people are most familiar with for understanding energy is the calorie. So I hope this was interesting, maybe in a trivial pursuit sort of way, but I think I needed to go over this and set a foundation for the rest of this content, which we'll talk about more world-shaking issues very soon, as I already begun to touch on them. Okay, well, with that, I hope you have a wonderful week or whatever until you watch the next episode. And I hope you keep coming back, leave comments or whatever. Um, love to hear from you, and keep coming back. And take care.